In this video, we're going to go over the guidelines for the internal assessment. This is for the new syllabus in May 2025. We're going to talk about our approach to the IA and then how to interpret the scoring rubric. As you're doing this internal assessment, this project, you want to think of it as this great opportunity to develop your inner sense of curiosity. So you're going to be carrying out this experiment and planning it out as well. So along the way, you're going to have some questions, some genuine questions where you ponder what's going to happen. And then later, you're going to have that satisfaction where you answer your own question, where you've carried out an experiment and you've answered your own question. That's curiosity. And curiosity is not just for science. If you're curious about people, you're going to be so much better socially. You're going to be much better liked because you're curious about people. You're delighted by people. It's enjoyable to be with people. In Buddhism, they talk about seek, find, hold, remain as being sort of the 4 steps to cultivating an inner quality. So to seek a quality, we could think about our past. Was there an instant in our past where we felt genuinely curious? And there probably was. So we want to get a glimpse of what curiosity felt like. That's seeking. And then finding is in the here and now. Can you find curiosity? So maybe while you're doing your IA, suddenly there'll be a moment of curiosity where you'll feel a genuine curiosity about something. Okay, so you found it within yourself in the here and now. Next step, can you remain in curiosity? So, for instance, could you remain for 15 minutes straight in a state of curiosity, say while you're doing your internal assessment? Could you stay there? And then finally is to remain in curiosity, to make curiosity a part of your being, so that really everything that you do in life you do with that sense of curiosity, and you find life that much more delightful because of it. The first question that students usually ask is, how big is the investigation? And we get clear guidelines on that. It's maximum up to 3,000 words. And that's about 11 pages double-spaced. That does not include graphs or tables or equations or your title page or references or footnotes or bibliography. They do want you to include that word count. And something you'd like to cultivate here would be your ability to be precise and concise. So be precise. Use the right words in the right situation. Use your scientific terms, etc. And then be concise. The worst type of IA is one that used 3,000 words, but everything that was said could have been done in 500 words. You don't get extra marks for extra words. So you want to be to the point. You want to say what's relevant. You want everything that you say to be coherent to your research question. So everything's tied together. It's a really important skill, not just in the essay, but in life, to pick out what is essential. What is it that belongs, and what is it that's fluff that you need to get rid of? The second question is usually, well, what can you do in the investigation? What's the investigation about? So overall, it's an investigation where you have to plan the investigation and then carry it out. So planning and design are part of the process. Most of the investigations in physics are going to be measurement based. So that means for your research question would be along the lines as, how does this independent variable affect this dependent variable? Or it could be actually measuring a physical quantity. So your research question would be something along the lines of, how accurately and precisely can such and such, say the acceleration due to gravity, be measured using such and such equipment. Many students do. There are many online simulations, so many students do use the simulations. That can be good work, especially if the simulation is paired with some physical measurements, so they can kind of be verified. The Typically, the problem with the simulations is that it's difficult to do the uncertainty analysis with the simulation. There are some data-based, some good data-based work. Often data is coming from the World Wide Web or the CERN. These different sites have lots of data that you can use. And this one is really measurement-based, but you can use a video analysis to do an investigation, which is particularly suitable for physics. And then the next question, how is it marked? It's marked on 4 different categories. Each is equally weighted, worth 6 marks each, adding up to a grand total of 24 marks. So the basic categories are research and design, which would approximately be the development of your research question, your method, and any background content, perhaps leading up to a hypothesis. Data analysis would include your charts and your calculations and your graphs. Conclusion, well, what do you conclude from your data? And then your evaluation would be writing about the limitations and strengths of your data and suggesting ways that the experiment could be improved for the future. The overall weighting percentage of the IA is 20%. That is, this IA will constitute 20% of your final overall IB mark. The first thing you're going to have to do, of course, is to choose a topic. And that's all about a sense of good fit. And we can think of the good fit in terms of both internal parameters and external parameters. On the internal side, you're going to ask yourself, does the topic, does it interest you? Because interest is really good energy, and you want all the energy, all the good energy that you can get. Secondly is to gauge your own abilities, to know thyself. Is this going to be too challenging of a topic for you, or is it not going to be challenging enough? You want that level where it's going to stretch you a little bit, but it's not going to overstretch you. On the more external side, is this lab, as you kind of look ahead and you plan ahead, is it going to be doable? In particular, are you going to be able to run the experiment that you want in a reasonable amount of time? And then how well does this experiment, this topic, how well does it fit the scoring criteria? So for instance, some labs, they won't do a very good job of showing off, say, your skills with uncertainties. So if you're really strong with uncertainties and you want to show that off, that won't be a good lab for you. And some labs aren't good for really showing off your, say, data manipulation skills. So you want to pick something that's very suitable to the scoring criteria. And no topic is going to fit all of these perfectly. You just have to go with what overall fits the best for you. The first scoring category is called research design. And I just want to circle a few words from the scoring rubric. And we'll kind of focus on them as we kind of flesh out what they're expecting you to do, what these things mean. So research question and context, method, data, and reproducibility. Now let's take a little look at them in more detail. In the scoring rubric, in that 5-6 box, there were 3 basic statements. So each of these columns corresponds to one of those statements. So the first statement had to do with the research question. You want a clear research question. And they're typically going to follow one of 2 templates. So if you're seeing how the dependent variable changes with an independent variable, the template would be how does the independent variable change or affect the dependent variable. And if you're doing, say, a measurement of the acceleration due to gravity, the template would be how accurately and precisely can G be measured using such and such equipment. Make sure your research question is focused, meaning somebody can read it and make sense of what's going on. So if you were just to say, how does the force affect the acceleration? nobody can make sense of that. But if you say, how does the force on a cart affect the acceleration of a cart, people can make sense of what's going on. It's a good idea to explicitly state your independent variable, your dependent variable, and your control variables. Now, the other thing you need to do is give context to your research question. And in physics, I believe there is a best way of doing that, and that is to make a prediction graph. And really a justified prediction graph. And I've made another video showing you how to do that. So you don't have to, in a lot of these IAs, in a lot of the experiments that you do, you're not going to have the physics background in order to derive a bunch of equations and make a prediction as to what it's going to be. But you can make a more general prediction graph as to what the shape of the graph of your independent versus dependent variable is going to look like. And if you do that, it just makes the whole essay so much more coherent, because in your conclusions you can refer back to your prediction, and you also know that you've given exactly the right background because you've made a prediction, you've made a justified prediction for your research question. So that's perfect. Okay, scoring criteria number 2, or statement number 2, was about how do you get good data. So in your methods section, what did you do to get good data? And that comes under 2 categories. The first is, how do you get sufficient data? So do you have enough increments of your independent variable, and do you have enough trials at each increment in your experiment? Did you vary your independent variable enough so that you can see variations in your dependent variable? And if you have some critical points in your graph, like a peak, a maximum in your graph, then do you have enough data in around that critical peak so that you can really see it? And then the other thing is, how did you get relevant data? So by relevant data, we mean essentially good data, meaning, let's say you assume there wasn't any friction in your experiment. Well, you might have had to take some steps to eliminate friction as much as possible. Or maybe you're doing a heat transfer experiment and you want to mitigate, lessen as much as possible the heat losses to the environment. So what sort of steps did you take so that your data is going to be good, relevant? And thirdly, in your method, can say another student in your class read over your method and then be able to reproduce your experiment? Did you give them enough details so that they can do that? And I think it's a good habit to think of writing for another student in your class rather than for your teacher. And to do so in a very practical way. If you think about writing for another student in your class so that they will understand, you'll write in a more natural way. And I often see very kind of complex writing that serves no purpose and is very unclear. And I think it's because students are trying to impress their teacher rather than communicate well. The second scoring category is data analysis. So let's read over those 3 statements in the 5-6 box. The first one says that the communication of the recording and the processing is clear and precise. The second statement, the recording and processing of data shows evidence of an appropriate consideration of uncertainties. And the third statement, the processing of data relevant to addressing the research question is carried out appropriately and accurately. So the first statement has to do with recording and processing your data in a precise and clear way. So the first thing you're going to need to do is put your raw data into a data table. And you want that to be well organized. And at least for those independent versus dependent variable experiments, this format here works really nicely. So in that first column, you've got the independent variable and the increments in the independent variable. In the top column, in that column heading, you can place the plus or minus and include the units with the plus or minus. So you've got both the uncertainty there and the units. Your trials can go across the page. The average of each trial can go in that second last column. And then in the final column, you can calculate the range divided by 2. You calculate the uncertainty as the maximum value across those trials minus the minimum value over 2. So that's a really effective, organized way to present your raw data. You want to do sample calculations as needed. Make sure you've got units where you need them on your graphs. Make sure you've got the units and the labels. You'd like a title for your graph as well. And make sure you're following proper notation for things like scientific notation. And generally, you just want to use conventional formats. So if you do some sample calculations, and you're probably going to need to, do it in a way that others can follow. So you kind of follow conventions. So for instance, in your data booklet, there's a way to present uncertainties, and you should use those formats. The other two statements in data analysis had to do with uncertainties and then a relevant and appropriate and accurate processing of your data. So for uncertainties, where you'd like to have uncertainties, and these are kind of taking it up a notch each time, you'd like to have uncertainties in your raw data. You'd like to have propagated uncertainties in your calculated values. You'd like to have error bars. And if you've linearized your data, you'd like to have the uncertainty in the slope and the y-intercept. Now, when they talk about relevant, appropriate, and accurate processing, well, is your data processing correct, or have you made mistakes? And then the second thing is, are all the calculations, all the graphs that you've done, is everything that you're doing, is it part of your answer to the research question, or is it something that's tangential? If it's something that's tangential, it's not relevant, and that'll knock your mark down. So just put stuff in your essay that answers your research question. So let's now take a look at the conclusions rubric. So there are two statements in the 5-6 box. We want a justified conclusion that's relevant to the research question and fully consistent with the analysis that has been presented. And secondly, the conclusion is justified through relevant comparison to the accepted scientific context. So there are two basic statements in the conclusion section. One had to do with the conclusions being justified and being relevant to the research question and being consistent with the data analysis. And the other had to do with placing your conclusions in context, meaning where does it fit into the larger body of physics knowledge? And the first thing I have to say to you here is that you're going to do a much better job with your conclusions if earlier in your project you had done a justified prediction graph. Because if you've done that, then your job becomes to compare and contrast your predicted results to your actual experimental results. And when I say compare and contrast, I'm talking about the graphical features. So for instance, does it have the same general shape? Does it have the same y-intercept, the same x-intercept? Does it have the same asymptotes, if there are any? And then where there are discrepancies between the prediction and the experiment, that's where you want to give a physical explanation for why those discrepancies are occurring. And they might be occurring because of a poor theoretical assumption, or it might be because something that's gone astray in your method. And when we talk about the conclusions being consistent with the data analysis, we're really talking about how have you interpreted your graphs. So the interpretation. And in terms of interpretation, I think the first warning I want to give students is don't say something like, as the independent variable increases, the dependent variable increases. So when the force increases, the acceleration increases. That's too vague of a statement. So a little warning, don't say as IV independent variable increases, the dependent variable increases. That's too vague. The common relationships that you're likely to encounter would be, well, no relationship at all. The dependent variable doesn't change. Proportional relationships, straight line through the origin. Linear relationships, straight line not through the origin. And I would say what else is common would be a curve in which it increases at an increasing rate, and a curve which increases at a decreasing rate. So just be precise about the relationships that you're seeing. Give as much information as you feel confident with. So do not assume. So what I'll often see is a student will get some data points and then they conclude, oh, well, it's a straight line. It's a linear relationship. But if they had more data near the origin, the actual relationship would have looked more like this and not a straight line. So you want to be honest. Don't state more than you've shown. Don't state less than what you've shown. Be honest. It should be an authentic search for truth. And as one last warning, with an experiment, we don't prove things. We verify things, and we might verify something with strong evidence, or we might just have a slight verification with weak evidence. So verify, do not prove. In terms of the second statement, where you give context to your conclusions, if you've done a justified prediction graph and then you gave physical explanations for your discrepancies, then those physical explanations are really putting your conclusions into context. So the most common and the best way to give context is to give physical explanation. So where do your conclusions fit into the larger body of physics knowledge? Now, another way to give context is if you can find some research, other people's experiments, that you can compare and contrast to your results. So nowadays, there's so much information on the internet that often we're able to find experiments that are related to our experiment. So compare to related experiments. And do take note of the quality of those comparisons. Are you comparing to a professional researcher, or are you comparing to another student? The third way of putting your results into context is when you have some numerical comparisons that you can make. So for instance, if you were measuring G, you could find the percent difference between the accepted value and your value. And then you'd like to state whether or not you were within experimental uncertainty of the accepted value. The evaluation section has two statements. The first statement has to do with you explaining the relative impact of weaknesses or limitations that are arising out of your method. And the second statement has to do with suggesting and explaining realistic improvements that are going to address the weaknesses and limitations of your experiment. So there was two statements in the conclusions. The first statement was about the impact of the weaknesses or the limitations. I always think it's a good idea to compare your uncertainties in the raw measurements to get a sense of their relative size. And in general, you'd like to have a sense of ranking as to how important each one of the weaknesses in your experiment was. So for instance, if one of your raw measurements had an uncertainty of 15% and the other had an uncertainty of 0.5%, then you really want to focus in when you suggest improvements on that 15% uncertainty and making that better. Most of your discussion is usually circling around assumptions that you made that weren't really true. So you assumed that there wouldn't be any heat losses to the environment, but actually there was. You assumed your pendulum was suspended from a point source, but actually the knot was moving around a bit. You assumed there's no friction in the experiment. You assumed that the object would fall straight down, but it didn't. So all of those are important to discuss. You want to consider whether you had sufficient data. Did the dependent variable vary enough that you could see the patterns that you were supposed to see? And then you'd like to address the question of how the data was affected. So for instance, did it shift upwards all the values of your dependent variable? That would suggest a systematic error. And it's important to consider whether your errors are systematic or random because they have different effects. A systematic error will shift things in one direction. A random error will not. A lot of your measurements and a lot of the weaknesses will have both a systematic and a random aspect to them. So for instance, maybe we have parallax in our experiment. So that shifts all our results in one direction. Maybe it makes all the measurements too large. But it doesn't shift them all by the same amount because there's a random aspect to it. So in your explanations as to how the data was affected, you do need to consider whether it's systematic or random. For your improvements, you want to suggest one specific realistic improvement for each significant weakness. And you really want to address the most significant weaknesses first. The suggested improvements do not need to be complicated. They can be simple. Just make sure that they're both realistic and specific. So don't be vague. Don't say use an electronic device when you mean a photo gate timer. Don't say use a release mechanism. Make a diagram of the release mechanism that you have in mind. Perhaps you'll think of two different improvements for one problem, and then you can discuss which one is likely to be the best of the two. My final words of advice come from my Facebook feed where I saw a video on how men could pick up women. And it went through a bunch of things that men do, individual things that men do that are successful at picking up women. They have their shoulders back. They have a strong grip. They speak in a low voice. So there was all these external symptoms of men who are successful. But if I imagine somebody sort of trying to follow those external symptoms, I think they're going to be very herky-jerky. And though it might eventually work out for them, what I think is really important is that you ultimately have the goal of embodying, say, confidence and attractiveness. So there needs to be kind of an internal goal that's going to produce these external symptoms. And it's the same way with the lab. I'm giving you, for the most part, a bunch of external symptoms of a good lab. But what you ultimately want to do is develop within yourself to embody on the deepest level the internal qualities that great lab writers have. So things like curiosity, an authentic search for truth, a desire to communicate clearly, etc. And so that'll be my final word for this video.
And that's all for today, folks. Thank you very much.